The scientific revolution was the emergence of modern science during the early modern period, when developments in mathematics, physics, astronomy, biology, including human anatomy, and chemistry transformed views of society and nature. According to traditional accounts, the scientific revolution began in Europe towards the end of the Renaissance era and continued through the late 18th century, influencing the intellectual social movement known as the Enlightenment. While its dates are disputed, the publication in 1543 of Nicolaus Copernicus's De revolutionibus orbium coelestium on the revolutions of the heavenly spheres, and Andreas Vesalius's De humani corporis fabrica on the fabric of the human body, is often cited as marking the beginning of the scientific revolution. By the end of the 18th century, the scientific revolution had given way to the age of reflection. The concept of a scientific revolution taking place over an extended period emerged in the 18th century, before the French Revolution, in the work of Bailly, who saw a two-stage process of sweeping away the old and establishing the new. Introduction. Advances in science have been termed revolution since the 18th century. In 1747, Clairaut wrote that Newton was said in his own lifetime to have created a revolution. The word was also used in the preface to Lavoisier's 1789 work announcing the discovery of oxygen. Few revolutions in science have immediately excited so much general notice as the introduction of the theory of oxygen. Lavoisier saw his theory accepted by all the most eminent men of his time, and established over a great part of Europe, within a few years from its first promulgation. In the 19th century, William Whewell established the notion of a revolution in science itself, or the scientific method, that had taken place in the 15th–16th century. Among the most conspicuous of the revolutions which opinions on this subject have undergone is the transition from an implicit trust in the internal powers of man's mind to a professed dependence upon external observation, and from an unbounded reverence for the wisdom of the past to a fervid expectation of change and improvement. This gave rise to the common view of the scientific revolution today. A new view of nature emerged, replacing the Greek view that had dominated science for almost 2,000 years. Science became an autonomous discipline, distinct from both philosophy and technology, and came to be regarded as having utilitarian goals. It is traditionally assumed to start with the Copernican Revolution, initiated in 1543, and to be complete in the grand synthesis of Newton's 1687 Principia. Much of the change of attitude came from Galileo, who championed Copernicus and developed the science of motion, and Francis Bacon, whose confident and emphatic announcement of a new era in the progress of science inspired the creation of scientific societies such as the Royal Society. In the 20th century, Alexander Koyré introduced the term scientific revolution, centering his analysis on Galileo, and the term was popularized by Butterfield in his Origins of Modern Science. More recently, historians of science have stressed the continuity that can be discerned from the late medieval period, and have cast doubt on the inherently progressive nature of science. Much of this reassessment follows the work of Thomas Kuhn, whose 1962 work The Structure of Scientific Revolutions emphasized that different theoretical frameworks such as Einstein's relativity theory and Newton's theory of gravity, which it replaced, cannot be directly compared. New ideas. The scientific revolution was not marked by any single change. The following new ideas contributed to what is called the scientific revolution, many of which were called revolutions in their own fields. The replacement of the Earth as center of the universe by heliocentrism. Deprecation of the Aristotelian theory that matter was continuous and made up of the elements earth, water, air, and fire, because its classic rival, atomism, better lent itself to a mechanical philosophy of matter. The replacement of the Aristotelian idea that heavy bodies, by their nature, moved straight down toward their natural places, that light bodies, by their nature, moved straight up toward their natural place, and that ethereal bodies, by their nature, moved in unchanging circular motions, with the idea that all bodies are heavy, and move according to the same physical laws. inertia replaced the medieval impetus theory that unnatural motion, forced or violent rectilinear motion, is caused by continuous action of the original force imparted by a mover into that which is moved. The replacement of Galen's treatment of the venous and arterial systems as two separate systems with William Harvey's concept that blood circulated from the arteries to the veins impelled in a circle and is in a state of ceaseless motion. Galileo Galilei. René Descartes with Queen Christina of Sweden. Many of the important figures of the scientific revolution, however, shared in the Renaissance respect for ancient learning and cited ancient pedigrees for their innovations. Nicolaus Copernicus, 1473-1543, Kepler, 1571-1630. Newton, 1642-1727, and Galileo Galilei, 1564-1642, all trace different ancient and medieval ancestries for the heliocentric system. In the axiom scholium of his Principia, Newton said, its axiomatic three laws of motion were already accepted by mathematicians such as Huygens, 1629-1695, Wallace, Wren, and others. While preparing a revised edition of his Principia, Newton attributed his law of gravity and his first law of motion to a range of historical figures. All those ancients knew the first law of motion, who attributed to atoms in an infinite vacuum a motion which was rectilinear, extremely swift and perpetual because of the lack of resistance. Aristotle was of the same mind, since he expresses his opinion thus, in Physics 4.8.215 and 19-22 speaking of motion, in the void in which bodies have no gravity, and where there is no impediment he writes, why a body once moved should come to rest anywhere no one can say. For why should it rest here rather than there? Hence either it will not be moved, or it must be moved indefinitely, unless something stronger impedes it. Isaac Newton, unpublished scientific papers of Isaac Newton. Although intimations of the concept of inertia are suggested sporadically in ancient discussion of motion, the salient point is that Newton's theory differed from ancient understandings in key ways, such as an external force being a requirement for violent motion in Aristotle's theory. The geocentric model was nearly universally accepted until 1543 when Nicolaus Copernicus published his book titled De revolutionibus orbium coelestium, and was still widely accepted into the next century. At around the same time, the findings of Vesalius corrected the previous anatomical teachings of Galen, which were based upon the dissection of animals even though they were supposed to be a guide to the human body. Andreas Vesalius, 1514-1564, was an author of one of the most influential books on human anatomy, De humani corporis fabrica, published in 1543. French surgeon Ambroise Paré, c.1510-1590, is considered one of the fathers of surgery. He was a leader in surgical techniques and battlefield medicine, especially the treatment of wounds. Influenced by the works of Italian surgeon and anatomist Matteo Reale du Colombo, c. 1516-1559, the anatomist William Harvey, 1578-1657, described the circulatory system. Hermann Boerhaave, 1668-1738, is sometimes referred to as a father of physiology due to his exemplary teaching in Leiden, and his textbook Institutions Medici, 1708. Antony van Leeuwenhoek, the first person to use a microscope to view bacteria. It was between 1650 and 1800 that the science of modern dentistry developed. It is said that the 17th-century French physician Pierre Fauchard, 1678-1761, started dentistry science as we know it today, and he has been named the father of modern dentistry. Pierre Vernier, 1580-1637, was inventor and eponym of the vernier scale, used in measuring devices. Evangelista Torricelli, 1607-1647, was best known for his invention of the barometer. Although Franciscus Vieta, 1540-1603, gave the first notation of modern algebra, John Napier, 1550-1617, invented logarithms, and Edmund Gunter, 1581–1626, created the logarithmic scales, lines, or rules, upon which slide rules are based. It was William Aldred, 1575–1660, who first used two such scales sliding by one another to perform direct multiplication and division, and thus is credited as the inventor of the slide rule, in 1622. Blaise Pascal, 1623–1662, invented the mechanical calculator in 1642. The introduction of his Pascaline in 1645 launched the development of mechanical calculators first in Europe, and then all over the world. The notion of mathematical probability was first initiated by Pascal, with his research in the games of chance. His later theory for binomial coefficient, or Pascal's triangle, was used as some of the foundation to Leibniz's infinitesimal calculus. He also made important contributions to the study of fluid, and clarified the concepts of pressure and vacuum by generalizing the work of Evangelista Torricelli. He wrote a significant treatise on the subject of projective geometry at the age of 16 and later corresponded with Pierre de Fermat, 1601–1665, on probability theory, strongly influencing the development of modern economics and social science. Gottfried Leibniz, 1646–1716, building on Pascal's work, became one of the most prolific inventors in the field of mechanical calculators. He was the first to describe the pinwheel calculator in 1685, and invented the Leibniz wheel, used in the arithmometer, the first mass-produced mechanical calculator. He also refined the binary number system, foundation of virtually all modern computer architectures. John Hadley, 1682–1744, was mathematician, inventor of the octant, the precursor to the sextant. Hadley also developed ways to make precision aspheric and parabolic objective mirrors for reflecting telescopes, building the first parabolic Newtonian telescope and a Gregorian telescope with accurately shaped mirrors. Denis Papin, best known for his pioneering invention of the steam digester, the forerunner of the steam engine. Denis Papin, 1647–1712, was best known for his pioneering invention of the steam digester, the forerunner of the steam engine. Abraham Darby I, 1678–1717, was the first and most famous of three generations of the Darby family, who played an important role in the Industrial Revolution. He developed a method of producing high-grade iron in a blast furnace fueled by coke rather than charcoal. This was a major step forward in the production of iron as a raw material for the Industrial Revolution. Thomas Newcomen, 1664–1729, perfected a practical steam engine for pumping water, the Newcomen steam engine. Consequently, he can be regarded as a forefather of the Industrial Revolution. In 1672, Otto von Guericke, 1600–1686, was the first human on record to knowingly generate electricity using a machine, and in 1729 Stephen Gray, 1666–1736, demonstrated that electricity could be transmitted through metal filaments. The first electrical storage device was invented in 1745, the so-called Leyden jar, and in 1749 Benjamin Franklin, 1706–1790, demonstrated that lightning was electricity. In 1698 Thomas Savery, c.1650–1715, patented an early steam engine. German scientist Georg Agricola, 1494–1555, known as the father of mineralogy, published his great work De Re Metallica. Robert Boyle, 1627–1691, was credited with the discovery of Boyle's law. He is also credited for his landmark publication The Skeptical Chemist, where he attempts to develop an atomic theory of matter. The person celebrated as the father of modern chemistry is Antoine Lavoisier, 1743–1794, who developed his law of conservation of mass in 1789, also called Lavoisier's law. Antoine Lavoisier proved that burning was caused by oxidation, that is, the mixing of a substance with oxygen. He also proved that diamonds were made of carbon, and argued that all living processes were, at their heart, chemical reactions. In 1766 Henry Cavendish, 1731-1810, discovered hydrogen. In 1774 Joseph Priestley, 1733-1804, discovered oxygen. Gottfried Leibniz, 1646-1716, refined the binary system, foundation of virtually all modern computer architectures. German physician Leon Hartfuchs, 1501-1566, was one of the three founding fathers of botany, along with Otto Brunfels, 1489-1534, and Hieronymus Bach, 1498-1554, also called Hieronymus Tragus. Valerius Cordus, 1515-1554, authored one of the greatest pharmacopoeias, and one of the most celebrated herbals in history, Dispensatorium, 1546. In his Systema Naturae, published in 1767, Carl von Linné, 1707-1778, catalogued all the living creatures into a single system that defined their morphological relations to one another, the Linnean classification system. He is often called the father of taxonomy. Georges Buffon, 1707-1788, was perhaps the most important of Charles Darwin's predecessors. From 1744 to 1788, he wrote his monumental Histoire naturelle, générale, et particulière, which included everything known about the natural world, up until that date. Along with the inventor and microscopist Robert Hooke, 1635-1703, Sir Christopher Wren, 1632-1723, and Sir Isaac Newton, 1642-1727, English scientist and astronomer Edmund Halley, 1656-1742, was trying to develop a mechanical explanation for planetary motion. Halley's star catalogue of 1678 was the first to contain telescopically determined locations of southern stars. Many historians of science have seen other ancient and medieval antecedents of these ideas. It is widely accepted that Copernicus's De Revolutionibus followed the outline and method set by Ptolemy in his Almagest, and employed geometrical constructions that had been developed previously by the Meirage school in his heliocentric model, and that Galileo's mathematical treatment of acceleration and his concept of impetus rejected earlier medieval analyses of motion, rejecting by name Averroës, Adam Pace, Jean Buridan, and John Philoponus' theory of impetus. The standard theory of the history of the scientific revolution claims the 17th century was a period of revolutionary scientific changes. It is claimed that not only were there revolutionary theoretical and experimental developments, but that even more importantly, the way in which scientists worked was radically changed. Ancient and medieval background. The scientific revolution was built upon the foundation of ancient Greek learning and science in the Middle Ages, as it had been elaborated and further developed by Roman/Byzantine science and medieval Islamic science. The Aristotelian tradition was still an important intellectual framework by the 17th century, although by that time natural philosophers had moved away from much of it. Ptolemaic model of the spheres for Venus, Mars, Jupiter, and Saturn. George von Purbach, Theorica Novae Planetarum, 1474. Key scientific ideas dating back to classical antiquity had changed drastically over the years, and in many cases been discredited. The ideas that remained, which were transformed fundamentally during the scientific revolution, include Aristotle's cosmology, which placed the Earth at the center of a spherical hierarchic cosmos. The terrestrial and celestial regions were made up of different elements which had different kinds of natural movement. The terrestrial region, according to Aristotle, consisted of concentric spheres of the four elements earth, water, air, and fire. All bodies naturally moved in straight lines until they reached the sphere appropriate to their elemental composition, their natural place. All other terrestrial motions were non-natural, or violent. The celestial region was made up of the fifth element, ether, which was unchanging and moved naturally with uniform circular motion. In the Aristotelian tradition, astronomical theory sought to explain the observed irregular motion of celestial objects through the combined effects of multiple uniform circular motions. The Ptolemaic model of planetary motion, based on the geometrical model of Eudoxus of Cnidus, Ptolemy's Almagest, demonstrated that calculations could compute the exact positions of the sun, moon, stars, and planets in the future and in the past, and showed how these computational models were derived from astronomical observations. As such, they formed the model for later astronomical developments. The physical basis for Ptolemaic models invoked layers of spherical shells, though the most complex models were inconsistent with this physical explanation. It is important to note that ancient precedent existed for alternative theories and developments which prefigured later discoveries in the area of physics and mechanics, but in light of the limited number of works to survive translation, in an era when many books were lost to warfare, such developments remained obscure for centuries, and are traditionally held to have had little effect on the rediscovery of such phenomena, whereas the invention of the printing press made the wide dissemination of such incremental advances of knowledge commonplace. Meanwhile, however, significant progress in geometry, mathematics, and astronomy was made in the medieval era, particularly in the Islamic world as well as Europe. New approaches to nature. Historians of the scientific revolution traditionally maintain that its most important changes were in the way in which scientific investigation was conducted, as well as the philosophy underlying scientific developments. Among the main changes are the mechanical philosophy, the chemical philosophy, empiricism, and the increasing role of mathematics. The mechanical philosophy. Aristotle recognized four kinds of causes, and where applicable, the most important of them is the final cause. The final cause was the aim, goal, or purpose of some natural process or man-made thing. Until the scientific revolution, it was very natural to see such aims, such as a child's growth, for example, leading to a mature adult. Intelligence was assumed only in the purpose of man-made artifacts. It was not attributed to other animals or to nature. In mechanical philosophy, no field or action at a distance is permitted. Particles or corpuscles of matter are fundamentally inert. Motion is caused by direct physical collision. Where natural substances had previously been understood organically, the mechanical philosophers viewed them as machines. As a result, Newton's theory seemed like some kind of throwback to spooky action at a distance. According to Thomas Kuhn, he and Descartes held the teleological principle that God conserved the amount of motion in the universe. Gravity, interpreted as an innate attraction between every pair of particles of matter, was an occult quality, in the same sense as the scholastic's tendency to fall had been. By the mid-18th century that interpretation had been almost universally accepted, and the result was a genuine reversion, which is not the same as a retrogression, to a scholastic standard. Innate attractions and repulsions join size, shape, position, and motion as physically irreducible primary properties of matter. Newton had also specifically attributed the inherent power of inertia to matter, against the mechanist's thesis that matter has no inherent powers. But whereas Newton vehemently denied gravity was an inherent power of matter, his collaborator Roger Coates made gravity also an inherent power of matter, as set out in his famous preface to the Principia 1713 second edition, which he edited, and contra Newton himself, and it was Coates's interpretation of gravity rather than Newton's that came to be accepted. See also entropic gravity. The chemical philosophy. Chemistry, and its antecedent alchemy, became an increasingly important aspect of scientific thought in the course of the 16th and 17th centuries. The importance of chemistry is indicated by the range of important scholars who actively engaged in chemical research. Among them were the astronomer Tycho Brahe, the chemical physician Paracelsus, the Irish philosopher Robert Boyle, and the English philosophers Thomas Browne and Isaac Newton. Unlike the mechanical philosophy, the chemical philosophy stressed the active powers of matter, which alchemists frequently expressed in terms of vital or active principles of spirits operating in nature. Empiricism. The Aristotelian scientific tradition's primary mode of interacting with the world was through observation and searching for natural circumstances through reasoning. Coupled with his approach was the belief that rare events which seemed to contradict theoretical models were aberrations, telling nothing about nature as it naturally was. During the scientific revolution, changing perceptions about the role of the scientist in respect to nature, the value of evidence, experimental or observed, led towards a scientific methodology in which empiricism played a large, but not absolute, role. By the start of the scientific revolution, empiricism had already become an important component of science and natural philosophy. Prior thinkers, including the early 14th century nominalist philosopher William of Ockham, had begun the intellectual movement toward empiricism. Under the influence of scientists and philosophers like Francis Bacon, a sophisticated empirical tradition was developed by the 16th century. Belief of natural and artificial circumstances was abandoned, and a research tradition of systematic experimentation was slowly accepted throughout the scientific community. Bacon's philosophy of using an inductive approach to nature, to abandon assumption, and to attempt to simply observe with an open mind was in strict contrast with the earlier Aristotelian approach of deduction, by which analysis of known facts produced further understanding. In practice, of course, many scientists and philosophers believe that a healthy mix of both was needed: the willingness to question assumptions, yet also to interpret observations assumed to have some degree of validity. By the end of the scientific revolution, the organic, qualitative world of book-reading philosophers had been changed into a mechanical, mathematical world, to be known through experimental research. Though it is certainly not true that Newtonian science was like modern science in all respects, it conceptually resembled ours in many ways. Many of the hallmarks of modern science, especially with regard to its institution and profession, did not become standard until the mid-19th century. Mathematization. Scientific knowledge, according to the Aristotelians, was concerned with establishing true and necessary causes of things. To the extent that medieval natural philosophers used mathematical problems, they limited social studies to theoretical analyses of local speed and other aspects of life. The actual measurement of a physical quantity, and the comparison of that measurement to a value computed on the basis of theory, was largely limited to the mathematical disciplines of astronomy and optics in Europe. In the 16th and 17th centuries, European scientists began increasingly applying quantitative measurements to the measurement of physical phenomena on the Earth. Galileo maintained strongly that mathematics provided a kind of necessary certainty that could be compared to God's with regard to those few mathematical propositions which the human intellect does understand. I believe its knowledge equals the divine, in objective certainty. Philosophy, i.e., physics, is written in this grand book, I mean the universe, which stands continually open to our gaze, but it cannot be understood unless one first learns to comprehend the language and interpret the characters in which it is written. It is written in the language of mathematics, and its characters are triangles, circles, and other geometrical figures, without which it is humanly impossible to understand a single word of it. Without these, one is wandering around in a dark labyrinth. Significance of the Revolution. Science in the Middle Ages was significant in establishing a base for modern science. The Marxist historian and scientist J.D. Bernal asserted that the Renaissance enabled a scientific revolution which let scholars look at the world in a different light. Religion, superstition, and fear were replaced by reason and knowledge. This quote needs a citation. James Hannam says that, while most historians do think something revolutionary happened at this time, the term scientific revolution is another one of those prejudicial historical labels that explains nothing. you could call any century from the 12th to the 20th a revolution in science, and that the concept does nothing more than reinforce the error that before Copernicus nothing of any significance to science took place. Despite some challenges to religious views, however, most notable figures of the scientific revolution including Nicolaus Copernicus, Tycho Brahe, Johannes Kepler, Galileo Galilei, Francis Bacon, René Descartes, Isaac Newton, and Gottfried Leibniz were devout in their faith. Some scholars see a direct tie between Christian metaphysics and the rise of science. This period saw a fundamental transformation in scientific ideas across mathematics, physics, astronomy, and biology in institutions supporting scientific investigation and in the more widely held picture of the universe. The scientific revolution led to the establishment of several modern sciences. In 1984, Joseph Ben David wrote, "Rapid accumulation of knowledge, which has characterized the development of science since the 17th century, had never occurred before that time. The new kind of scientific activity emerged only in a few countries of Western Europe, and it was restricted to that small area for about 200 years. Since the 19th century, scientific knowledge has been assimilated by the rest of the world." Many contemporary writers and modern historians claim that there was a revolutionary change in worldview. In 1611 the English poet, John Donne, wrote, "The new philosophy calls all in doubt. The element of fire is quite put out, the sun is lost, and the earth, and no man's wit can well direct him where to look for it." Mid-20th century historian Herbert Butterfield was less disconcerted, but nevertheless saw the change as fundamental. Since that revolution turned the authority in English not only of the Middle Ages, but of the ancient world. Since it started not only in the eclipse of scholastic philosophy, but in the destruction of Aristotelian physics, it outshines everything since the rise of Christianity, and reduces the Renaissance and Reformation to the rank of mere episodes, mere internal displacements within the system of medieval Christendom. It looms so large as the real origin both of the modern world and of the modern mentality, that our customary periodization of European history has become an anachronism and an encumbrance. More recently, sociologist and historian of science Stephen Chapin opened his book, The Scientific Revolution, with the paradoxical statement, "There was no such thing as the scientific revolution, and this is a book about it." Although historians of science continue to debate the exact meaning of the term, and even its validity, the scientific revolution still remains a useful concept to interpret the many changes in science itself. Scientific developments. Key ideas and people that emerged from the 16th and 17th centuries. First printed edition of Euclid's Elements, in 1482. Nicolaus Copernicus, 1473-1543, published on the revolutions of the heavenly spheres, in 1543, which advanced the heliocentric theory of cosmology. Andreas Vesalius, 1514-1564, published a humani corporis fabrica, on the structure of the human body, 1543, which discredited Galen's views. He found that the circulation of blood resolved from pumping of the heart. He also assembled the first human skeleton from cutting open cadavers. Franciscus Vieta, 1540-1603, published an Artem Analycatemisagogy, 1591, which gave the first symbolic notation of parameters in literal algebra. William Gilbert, 1544-1603, published on the magnet and magnetic bodies, and on the great magnet the Earth, in 1600, which laid the foundations of a theory of magnetism and electricity. Tycho Brahe, 1546-1601, made extensive and more accurate naked eye observations of the planets in the late 16th century. These became the basic data for Kepler's studies. Sir Francis Bacon, 1561-1626, published Novum Organum in 1620, which outlined a new system of logic based on the process of reduction, which he offered as an improvement over Aristotle's philosophical process of syllogism. This contributed to the development of what became known as the scientific method. Galileo Galilei, 1564–1642, improved the telescope, with which he made several important astronomical discoveries, including the 4 largest moons of Jupiter, the phases of Venus, and the rings of Saturn, and made detailed observations of sunspots. He developed the laws for falling bodies based on pioneering quantitative experiments which he analyzed mathematically. Johannes Kepler, 1571–1630, published the first 2 of his 3 laws of planetary motion in 1609. William Harvey, 1578–1657, demonstrated that blood circulates, using dissections and other experimental techniques. René Descartes, 1596–1650, published his Discourse on the Method in 1637, which helped to establish the scientific method. Antony van Leeuwenhoek, 1632–1723, constructed powerful single-lens microscopes and made extensive observations that he published around 1660, opening up the micro-world of biology. Isaac Newton, 1643–1727, built upon the work of Kepler and Galileo. He showed that an inverse square law for gravity explained the elliptical orbits of the planets, and advanced the law of universal gravitation. His development of infinitesimal calculus opened up new applications of the methods of mathematics to science. Newton taught that scientific theory should be coupled with rigorous experimentation, which became the keystone of modern science. Theoretical developments. Portrait of Johannes Kepler. In 1543, Copernicus' work on the heliocentric model of the solar system was published, in which he tried to demonstrate that the sun was the center of the universe. Few were bothered by this suggestion, and the Pope and several archbishops were interested enough by it to want more detail. His model was later used to create the calendar of Pope Gregory XIII. For almost 2 millennia, the geocentric model had been accepted by all but a few astronomers. The idea that the Earth moved around the Sun, as advocated by Copernicus, was to most of his contemporaries doubtful. It contradicted not only empirical observation, due to the absence of an observable stellar parallax, but also Aristotelian philosophy. The discoveries of Johannes Kepler and Galileo gave the theory credibility. Kepler was an astronomer who, using the accurate observations of Tycho Brahe, proposed that the planets move around the Sun not in circular orbits, but in elliptical ones. Together with his other laws of planetary motion, this allowed him to create a model of the solar system that was an improvement over Copernicus' original system. Galileo's main contributions to the acceptance of the heliocentric system were his mechanics, the observations he made with his telescope, as well as his detailed presentation of the case for the system. Using an early theory of inertia, Galileo could explain why rocks dropped from a tower fall straight down even if the Earth rotates. His observations of the moons of Jupiter, the phases of Venus, the spots on the Sun, and mountains on the Moon all helped to discredit the Aristotelian philosophy and the Ptolemaic theory of the solar system. Through their combined discoveries, the heliocentric system gained support, and at the end of the 17th century it was generally accepted by astronomers. Kepler's laws of planetary motion and Galileo's mechanics culminated in the work of Isaac Newton. His laws of motion were to be the solid foundation of mechanics. His law of universal gravitation combined terrestrial and celestial mechanics into one great system that seemed to be able to describe the whole world in mathematical formulae. Not only astronomy and mechanics were greatly changed. Optics, for instance, was revolutionized by people like Robert Hooke, Christian Huygens, René Descartes, and, once again, Isaac Newton, who developed mathematical theories of light as either waves, Huygens, or particles, Newton. Similar developments could be seen in chemistry, biology, and other sciences, although their full development into modern science was delayed for a century or more. Contrary views. Not all historians of science are agreed that there was any revolution in the 16th or 17th century. The continuity thesis is the hypothesis that there was no radical discontinuity between the intellectual development of the Middle Ages and the developments in the Renaissance and early modern period. Thus the idea of an intellectual or scientific revolution following the Renaissance is, according to the continuity thesis, a myth. Some continuity theorists point to earlier intellectual revolutions occurring in the Middle Ages, usually referring to either a European Renaissance of the 12th century or a medieval Muslim scientific revolution, as a sign of continuity. Another contrary view has been recently proposed by Aaron Balla in his dialogical history of the birth of modern science. Balla proposes that the changes involved in the scientific revolution, the mathematical realist turn, the mechanical philosophy, the atomism, the central role assigned to the sun and Copernican heliocentrism have to be seen as rooted in multicultural influences on Europe. He sees specific influences in Alhazen's physical optical theory, Chinese mechanical technologies leading to the perception of the world as a machine, the Hindu-Arabic numeral system, which carried implicitly a new mode of mathematical atomic thinking, and the heliocentrism rooted in ancient Egyptian religious ideas associated with Hermeticism. Balla argues that by ignoring such multicultural impacts we have been led to a Eurocentric conception of the scientific revolution. However, he clearly states, the makers of the revolution, Copernicus, Kepler, Galileo, Descartes, Newton, and many others, had to selectively appropriate relevant ideas, transform them, and create new auxiliary concepts in order to complete their task. In the ultimate analysis, even if the revolution was rooted upon a multicultural base, it is the accomplishment of Europeans in Europe. Critics note that lacking documentary evidence of transmission of specific scientific ideas, Balla's model will remain a working hypothesis, not a conclusion. A third approach takes the term Renaissance literally, as a rebirth. A closer study of Greek philosophy and Greek mathematics demonstrates that nearly all of the so-called revolutionary results of the so-called scientific revolution were in actuality statements of ideas that were in many cases older than those of Aristotle, and in nearly all cases at least as old as Archimedes. Aristotle even explicitly argues against some of the ideas that were demonstrated during the scientific revolution, such as heliocentrism. The basic ideas of the scientific method were well known to Archimedes and his contemporaries, as demonstrated in the well-known discovery of buoyancy. Atomism was first thought of by Leucippus and Democritus. This view of the scientific revolution reduces it to a period of relearning classical ideas that is very much an extension of the Renaissance. This view of the scientific revolution does not deny that a change occurred, but argues that it was a reassertion of previous knowledge, a renaissance, and not the creation of new knowledge. It cites statements from Newton, Copernicus, and others in favor of the Pythagorean worldview as evidence.